So now I think we'll move on to our next talk, which is from Phil Metzger from the University of Central Florida. He's going to talk to us about deep reduction of energy requirements for lunar ice extraction, which will take us into an icy themed 3 talks. Go ahead, Phil.
Okay, hello. It's great seeing everybody. I was going to try to use the remote clicker, but I don't know if it's working. James, do you know?
You'd be the first person to make it work today. So if you're uncertain, I'd suggest just doing it the old school way.
Yeah. Okay, so it's great seeing everybody, and the organization of the conference is fantastic, but I do hope we can see each other in person next year. So if we can start with the charts, I'm going to be talking about a NIAC, NASA NIAC project that we just finished. This is, the project was called Aqua Factorem, which means water maker. So if we can go to the next chart. Next chart, please. So the goal of this project was to reduce the infrastructure cost of mining on the moon in order to improve the business case. So it was really a business-oriented project. And the key insight is that volatiles are by definition elements that flee from energy, whereas rocket fuel is stored energy. And so the infrastructure cost is driven by the energy infrastructure to bring those two together. And so a minimum viable business would be something that minimizes the transportation of energy. Next chart, please. So the strategy was to develop a system that can be delivered to the moon on a single lander, maybe a 10-ton payload like on the Blue Moon lander from Blue Origin. It should be a system that begins to develop revenue immediately, serving customers immediately. That way the technologies can be matured operationally on the moon. And it should be a system that has smooth scale up to large scale while it's making profit. And the real goal is not the profit, but the optimism that would be created during the scale up process so that it can motivate subsequent rounds of investment, so that each round of investors can have an exit in a reasonably short amount of time until the system is very profitable. Okay, next chart. The study team members were myself, Dr. Daka Sapkota, who is a postdoc working with me, Jack Fox, who's I worked with at NASA, and Nicholas Bennett from the Australian Center for Space Exploration Research. My cat just knocked over the lighting. Hang on one second. Darn cat. So sorry for that. Cats. Okay, next chart, please. Okay, so we're gonna have to click a bunch of times. So just keep clicking, please. So the current approach is, okay, stop there. The current approach is that a spacecraft operator will use an expendable launcher to send the spacecraft into geostationary transfer orbit. And then over about 6 to 12 months, using an electric thruster, it'll slowly raise the perigee. This is cheaper than using an upper stage, but it takes 6 to 12 months, so the spacecraft operator will lose about $100 million in revenue from their spacecraft, all the while they have full operational costs of the spacecraft. Next click, please. So the new approach is going to be to launch a space tug directly from the surface of the moon. This is the minimum viable business case. So click, please. Then with aero braking, click again, please. It can go into geostationary transfer orbit. Just keep clicking. Rendezvous with the spacecraft, boost it in 1 day, and then return to the surface of the moon to refuel. And so the idea is you can recover $100 million in revenues from that spacecraft. And so that provides the window that we're going to try to work in for the business case. And I have to hold on to the lighting because that cat is wild. Okay, next chart, please. Okay, so the system architecture will look like this. It'll be an excavation-based approach where we're not going after the best resources on the moon, we're going after the easiest resources. And so Tony Colaprete, who's going to speak soon, has a system where he's classified the resources And this would be a type 2 resource where it's 1 to 2% water ice with a shallow overburden. But the key issue is that it's driving in and out on shallow slopes over relatively short distances between permanently shadowed and permanently lit regions. And this would enable a hauling-based architecture. But in order to make a hauling-based architecture viable, you have to drastically reduce the hauling load. So this means we need beneficiation of the ice. And the next chart, we'll talk about that. So the geological insight is that the ice on the moon really ought to be granular, and it really ought not to be polymineralic with ice bonded to lithic grains, although there will be some of that. The processes on the moon that we know do not support that sort of a physical state of the ice. Bombardment is the dominant geological process. There is vaporization, but we have experience with vaporized material. It does create a coating on the grains, but that coating in the Apollo samples does not create any significant bonding because the fracturing dominates over the vapor deposition bonding. And also the agglutination process will not work for water ice because when you consider the vapor pressure and the thermodynamics of water compared to lithic materials, an agglutinous-sized droplet will vaporize in a nanosecond. So there's really no geological process or model that would support the idea of having ice physically bonded to lithic grains. Next chart, please. The data from the LCROSS mission suggests 20 micron sized particles of ice. The Moon Mineralogy Mapper suggests 70 micron particles on the surface. And so I've developed several models by analogy to the Apollo samples and based on the data that we have. And I've used these ice grain size models in the subsequent modeling. Next chart, please. So this is the invention. The challenge with trying to do beneficiation on the moon is that the soil is highly weathered, and that weathering alters the surface properties and the magnetic properties of the soil. And so in order to beneficiate, you have to work around the weathering. And I'm going to go through these process stages in the next couple of charts. So let's go to the next chart, please. So the first stage is de-dusting. The idea in the de-dusting stage is because the superparamagnetism dominates in the fine particles, whereas surface area is dominant. And so you need a high shear stress flow to remove the dust from the surfaces of the other grains. Now, I'm showing you the modeling in this chart. I'm not showing the experimental work we've done, but some of this technology is at TRL3, some is at TRL5. When you separate the dust from the coarse fraction, it does not give you a concentration of ice, which is represented by the gray bar in these bar charts, but it does separate out the dominantly superparamagnetic material. Next chart. So then the next stage would be to process the, and this is what the model looks like if you use a highland soil using ice model 1, and the next chart, please, is a highland soil with ice model 4. So then after doing the dust separation, you don't want to throw the dust away because a significant fraction of the ice will be in both material streams. So then we designed a magnetic separation stage in the pneumatic transport, and this will give you a fine stream which is very largely dominantly ice. The next chart, please. You can throw away the magnetic dust unless you have another purpose for it, and there are other purposes for it. Next chart, please. Then processing the coarse materials. Again, the next stage would be a magnetic separation because you can remove 70% of the mass, which makes the subsequent downstream stages more effective. Next chart, please. Again, throwing away the coarse fraction. And then the next stage is to run it through pneumatic size separation. Now, this does not give you any significant concentration of the ice, but what it does do on the next click is it gives you a separation of the particle sizes.
You have 5 minutes.
Thank you. So by separating the coarse versus the lithic fraction and the ice fraction in their particle sizes, then in the subsequent stage, next chart, in each of these material streams, next chart, please. You can use vibrational separation or a version of that to get a good separation, a complete separation of the ice from the lithic fraction. You could use electrostatic separation because that should also be very effective because of the high tribocharging difference of ice versus all the other materials. But a vibrational separation is quite adequate. Okay, next chart. So the end result is in our architectural roll-up, we did a full study of the architecture. It predicts about 3 tons of hardware to the moon is adequate to separate the ice from the soil. And with only 50 kilowatts of power, this can produce 27.9 tons of water annually, which is enough to boost 4 geostationary satellites going directly from the moon and back. And so the startup cost would be 213 million US dollars or 178 million euro. And this could produce up to 400 million US dollars or 330 million euro annual revenue. So there is a potential for a business case right from the start. So in our final chart, next chart, please. Next chart, please. So we believe we have successfully demonstrated an architecture that will lower the requirement for startup investments. This can produce revenue from the very first landing on the moon, and it can scale up smoothly. This could be revolutionary for space resources. So my university has patented the technology, and it's available for commercial licensing. Next chart, please. I want to acknowledge the funding from a grant from the NASA Innovative Advanced Concepts Project, and you can contact me if you'd like more information. So thank you so much for your time today.
That's great. Thank you very much, Phil. 2 quick questions. So the first one, actually, most of the questions are actually for your cat, Phil. But the questions that are for you. So the first is, do you see losses in water due to all the agitation in the separation?
Yeah, that's a great question. And there needs to be a lot of work developing the technology. So we can't be too specific about these things. You know, like I said, these are around TRL3 to TRL5. But if you're working in a PSR, then you have a great environment for using radiators to shed heat from your spacecraft. Most people are worried about the spacecraft becoming too cold. So we believe that it should be very possible to shed heat as you're operating and keep the resource cold. The beneficiation will need to be a batch process because we're using pneumatics. And after you've transferred it into a closed container, you can then transport it out in a closed container to avoid losses as you're going out to where you can do the water cleanup.
Okay, that's great. Thanks. And we just have one more question before we move on, which was a couple here. So you said that you only need 50 kilowatts of power. There's a question of, have you made any idea already on how to provide that power? Where might that come from?
Yeah, so in the concept that we analyzed, we assumed it would be a solar array on a mast that would be deployed, and 50 kilowatts is very feasible using that deployment mechanism. So as we said, this entire system, including the power systems, could be delivered on a single lander to the moon.
That's great. So thanks very much, Phil. Much appreciated. Thanks for your talk, and thanks to the cat.